Hello, and welcome to another episode of My 2 Cent. My name is Paul Emerson, and I'll be giving you my 2 cent. Today's topic is going to be Taxonomy of Numbers. So this is going to be an introduction to, this is going to be an introduction into the foundation of mathematics. And from this, all other disciplines will proceed. So, Taxonomy of Numbers. What is a number? In arithmetic, what is a number? A number is an arithmetic value expressed by a word, symbol, or figure representing a particular quantity and used in counting and making calculations and for showing orders in a series or for identification. The other simplest definition is a quantity or amount. So, most of us are taught numbers in school where our young adolescent mind doesn't ask too many questions. We just basically follow what we're told. So, the numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 for a total of 10 characters. Alright? This is a number line, and then we'll put -1 here. I like using this one because it's not I. So -1 to 1 to 0. So here to here, somewhere in the middle, will be 0.5. I'm sorry, it would be -0.5, and somewhere here would be +0.5. Okay, now with this foundation, there are 3 taxonomic numbers. There are 3 basic types of numbers. There are a lot of numbers that are listed in mathematics. However, for the sake of this video, a number is a quantity, not an operation. A lot of numbers that we're giving are operations and not in of themselves numbers. So the quantities that do not require this plus this equals that, whatever quantity we define as a number, which is the result of some operation, excuse me, it's not part of the taxonomy of numbers. Oh, that's what this is for. So, with that understanding, there are roughly 3, and if there are other ones that you can think of that are not on my list of 3, let me know in the comments. There are 3 basic numbers. And those numbers are the whole numbers / real numbers, the integers, and the decimals, so that we can avoid ambiguity. And I'm pretty sure I spelled that wrong. I apologize for not being able to spell. Whole numbers are the counting numbers that we see listed here. Integers are also the counting numbers that we see here. But integers differ from just the whole numbers because they include the positive and negative values as well. The decimals are, how do I want to say this? The decimals are the sum of the fractions. This is an operation, as I've listed earlier, as I communicated earlier. For the sake of the taxonomy of numbers, any numerical value that is the subset of a operation is not, for the sake of this video, a number. So a fraction is a operation, when you solve the operation, you get the actual number. That's how it's going to work. So the three types of numbers we use in a Dewey Decimal System of 10 characters to represent all of our numerical quantities, that's those three right there. That's how this is gonna be the foundation. So from this, we need to move into operations. And to move into operations, I want to cover syntax. We deal with a lot of parentheses, exponents, multiplication, division, addition, subtraction. Please excuse my dear Aunt Sally, Pemdas. There's a lot of different terminologies for it. But there's something deeper about mathematics that is lost in translation in schools, and that is this equal sign. The equal sign is the absolute authority in mathematics. There are two basic representations of this symbol. I will call this one the open equal sign, and I'll call this one the closed equal sign. So something is either equal or not equal. And in mathematics, if I were to say 3 plus 5 is not equal to 8, I have just done the problem wrong, because 3 plus 5 equals 8. So the equal sign tells me that the equation is wrong. If I were to say 5 plus 9 is not equal to 11, the statement is true, so the problem is true. We lose this part of math through our creativity. It is because of our creative mind that we are not able to deal with the logic. So when you write 1 plus 1 equals 2, this is always true if you follow the proper syntax, because math is designed to be a story problem, even though we leave out the actual language itself. That is why the rules of Pemdas are important when solving the equations, because without them, you really don't know what position to take when trying to evaluate the actual equation. For example, 1 plus 3 times 4 should be 1 plus 3 times 4, which would give you 16, right? But let's say we do 1 plus 3 times 4 this way with the order operation. What this is doing is it's telling us how the numerical values are being quantified. Math is a set system. It took a minute. Let me see if I can remember the point I was making. Okay, so Pemdas. If you take the time to understand how math is an operation based on sets, then what you have is we do math. We follow a particular order when we do math. And it has a lot to do with the nature of real numbers. On the number line, I'll make a very small one here. We say this is the right side and this is the left side. So if I say if I say 1 plus 1, then I'm saying 1 plus 1 equals 2. So I'm implying that I'm moving through space and changing from this one to this one. If I say that I have 1 plus 2, then I'm moving through space 2 times, and I'm going to get 3. So 1 plus 1 equals 2. 1 plus 2 equals 3. Now, if I was to say that 2 plus 1 equals 3, then I'm starting at 2, and I'm going to move inherently to the right. So 2 plus 1 equals 3. If I was to say 2 minus 1 equals 1, then I'm saying that I'm going to start at 2, and because it's a negative value, I'm going to inherently move left 1 to arrive at the destination of 1. So when you're dealing with Pemdas, as an unspoken rule, is a relationship between numerical values as they apply to the real world. If I have $1 and then someone else gives me $3, and then I get that whole quantity 4 times, how many dollars do I have? So you can do it. If I was an accountant and I was a little shady, then I could just go, what would be the most effective way to do it? The correct way is to understand there's parentheses here. 3 times 4 will give you 12, plus 1 will give you $13, right? But if I was shady, then I would just be like, I'm going to just read it this way. 1 plus 3 times 4, I'm going to go ahead and, instead of you giving me $3 4 times, instead of giving me $3 4 times, you're going to give me $4 4 times. So now we arrive at 1 plus 3, which equals 4, times 4, which gives us 16. So the real world application requires Pemdas. For numbers to make sense and apply to reality, you have to follow the order operations. And it is my strong belief, after spending a lot of time contemplating Pemdas, that this order operations was built on a rigorous foundation of testing and proving the numerical validity of numbers always operating properly when they are described with real world sets of actual objects. Not numbers. Numbers are symbols that represent some idea. If I am a farmer and I grow apples and I harvest 100,000 apples and I want to sell them consistently and fairly to people, I believe that practice over thousands of years in human culture has resulted in the understanding of Pemdas. Because if I have 2 apples, if I have 2 baskets of apples and each basket has 2 apples in it, then I have 4 total apples, right? I mean, that's, if I have 10 baskets of apple and each basket has 7 apples in it, then I have 70 apples total. 10 times 7. You go left to right for addition and subtraction. You go up and down for multiplication and division. That's the way the set system has always worked. And that's the way the universe describes it as working. And humanity can come up with ways to extrapolate and go beyond the surface of our reasoning when it comes to our interpretation of mathematics. And we can engage in numbers that have no practical application for the common everyday life. But as we see more and more as our technology advances and evolves, that a lot of these principles that we did learn in school are now applicable in everyday work settings, financial settings, or however, whatever terminology you want to use. So with that being said, I want to go over very briefly the operations. The operations are addition, subtraction. Let's pin it down. Addition, subtraction, multiplication, division. Oh, that shouldn't have been a D. And division. Addition, subtraction, multiplication, division. Addition is the same as saying moving to the right by some value. Again, I know you can't read this, I'm just doing it because it's entertaining. And then subtraction is moving to the left by some value. These symbols mean just copy that information down. It's a shortcut from a time frame before copy and paste on computers. And then multiplication is moving a set to the right by some value. And it would probably be more accurate to say moving some number of sets. Of sets to the right by some value. Division is a little bit trickier to describe because it is the opposite operation of multiplication. It is not as intuitive as just doing the opposite. To divide, you take the equality. Okay, let's try it this way. Let's try it. Let's see if this will work. One of my favorite numbers is 2 because 2 plus 2 is equal to 2 times 2. It's one of my favorite numbers for that very reason. 2 plus 2 is equal to 4. 2 times 2 is also equal to 4. Division is how many numbers of 2's are inside of 4. How many of this number is inside that number? That's the foundation of division. 3 plus 3 equals 6. 3 times 3 equals 9. There are 3 nines. There are 3 number 3's in the number 9. There are 2 number 3's in the number 6. There are 2 number 2's in 4. No matter how you look at it, 2 plus 2 equals 4, and 2 times 2 equals 4. This is the only time that it's that you get that statement. I don't know any other numbers that do that. I mean, they could exist, but I highly doubt that they do. So what was the point I'm making? So to evaluate division, you have to say this plus this plus this equals 9. So I guess if you wrote it as a mathematical equation, it would be nx nx equals y. A number times, that wouldn't work either. I don't know. I'll have to come up with a better description. But most people pretty much intuitively understand what division means. Once I come up with a more simplified version of explaining it, I'll share it. But for right now, it's best described as the opposite of multiplication, even though it's not as intuitive. Because, as I just shown you, 3 times 3 equals 9. Same way that 2 times 2 equals 4. But 3 plus 3 does not equal 9, the same way that 2 plus 2 equals 4. But you ask yourself the same question. How many 3's are in 9? How many 2's are in 4? How many of a number is equal? How many of a number is inside of a number? How many of a number is inside of a number? And that's basically the principle, foundational principle of division. Now, lastly, let's try to deal with some of these other numbers. And I'm not 100% on how to approach these. You have, well, before I do that, I want to discuss, excuse me, before I do that, I want to discuss decimals. Decimals, I know I have it written down somewhere. I guess I don't. So I'm going to spell it incorrectly. Decimals. Decimals are, okay, what's this number? 1001, right? And this one's 100. And this one's 111. Decimals, remember the right, the left to right. That's the way we read our mathematics. We read them left to right. So you start on the left side, and you move to the right side to read the number. So 1001, 100, 111. Because you have your thousands place, your hundreds place, thousands, hundreds, tens, and ones. So thousands, hundreds, tens, and ones are your place values. The decimal is always the ones value. It's always the ones value. To the left of the decimal is always the ones value. So wherever the decimal is, to the left of it, that's where you will find the ones value. So if you have a string of numbers, no matter how big it is, you look at that number and you say, that's a really big number. Ones, tens, hundreds, thousands, 10,000s, 100,000s, ones, tens, hundreds, thousands, 10,000, 100,000, millions, 10 million, 100 million, a billion. A billion numbers. But as soon as you do something like that, that becomes your ones value. So this number to the left of the decimal is the ones place value. So all these numbers become decimal numbers. So now you have 1,036. You went from 1 billion to 1,036 with a lot of tenths, hundreds, thousands, 10,000s, 100,000s, millions. And there's other fancier terms for that. But that pretty much represents the decimal. So this is a decimal. We don't write it this way because there's no reason to. This is also a decimal. You can put as many zeros in front and behind the zero as you want, but it still is equal to 0. You can put an equal sign on this side too, and it would still equal 0. Yeah, I mean, that's just the way the syntax of math works. So that's the decimal. The reason why I wanted to cover the decimal is because I wanted to move into how numbers differ from the values we define, the values that mathematics define as numbers, but are actually operations. The best example with relationship to transitioning from decimals is fractions. So you have fractions, which are actually symbols of division, whose values typically, but not always, are associated with the value of 100. So it is understood that the fraction is always equal to a relationship of 100. And what I mean by that is, well, no, I guess that's not true. Because to be honest, the only time you get a relationship of 100 with a fraction is when the number is over 1. If the number is over 5 tenths. I mean, that's still, well, I'll do a video exclusively on fractions later. As to not confuse, I'll do a video exclusively on fractions. But every fraction is a division problem. This fraction, because of my experience with math, I know it is equal to 1/2, which is equal to half of 100. So it's half of this 1. So you would divide this 1 by half. You would divide 1 divided by 2, which would give you 0.5. Because 0.5 plus 0.5 equals 1.00. Because 50 plus 50 is 100. The decimal point is here, so when you add this 5 to this 5, you get a 1 to the left of the decimal. That'll give you 1.0, which will give you 1. If you divide 1 under 4, and this is why my original premise was that fractions are usually associated with the value of 100, but it's not true. It's only usually true when the number in the numerator is 1. So 4 divides into 1 is the decimal point to 5. This is an operation. This is a number. The operation of when you solve the operation for a fraction, get the decimal. And I think to avoid too much circular logic, I'm going to structure a more concrete demonstration for fractions. Fractions, percentages, 1/4 percentages, 35%, square roots, square roots, roots or exponents. These are all values that, when viewed, are equations. 35% would be a number if this wasn't an operation. So 35%, technically 35 is just a number, but the percent sign is an operation. It's telling you to perform some operation. So I'm going to spend another day or two understanding this stuff and a more refresher. I'm going to do a refresher on it. And then once I'm done with my refresher, I will get back to you. If you have any comments whatsoever, please leave them in the bottom of the video. That'll help me understand what the target audience is looking for, what information will help you understand math better, what principles you would like to cover. I plan on covering everything. I plan on researching the subject matters before I speak. I will guarantee you unequivocally that I will make mistakes on camera, because I strongly believe that making mistakes is part of the learning process. And if you are too afraid or too much of a coward to advance through your mistakes when you're trying to learn, that you will stagnate your own education. You can never learn without making the errors and accepting your failures. So I will be the representative of the fact that you can solve a problem wrong and erase it and redo it correctly. Because if you are wise enough to be able to identify your own errors, then you have already shown yourself that you are intelligent. If you need a teacher or an instructor to tell you, oh, that's not right, you're still learning. And as always, my name is Paul Emerson. I just give you my 2 cents.